Welcome to Study Loop.
This is a basic introduction into paper chromatography. So when you're given a mixture of compounds, sometimes you want to see what individual analytes are involved in that mixture. And paper chromatography is a very simple way to do that. So in this case, we have two vegetable dyes. One is blue and one is red. And we did two different experiments, A and B. And we want to know which one did a better job and also how can we compare them to see which one is the better paper chromatography method. So we have A, where we see just one dot on this piece of paper, and basically you add the dye at the bottom of the paper, and then you dip the very bottom of this paper into a solvent, say ethanol or acetone or water, and then as that water creeps up through capillary action on the paper, the dye will move with it. So here we have a purple dot, which indicates that the red and blue components did not separate. And then on the B side, we have both a blue and a red dot. And this is very common to see more of like a circle at the bottom and then a tail going upward. So basically, B is the better paper chromatography method because whatever solvent was used was able to separate the individual components based on their how much they like that solvent and want to stay in the solvent phase. So a more quantitative way to think about this is something called the retention factor. So the retention factor is basically how good it is at staying in the solvent as it moves up the paper. And it's calculated pretty basically with distance traveled by one specific component of the mixture or analyte over distance traveled by the solvent. So say the solvent traveled all the way up here. We have our analyte distances here. So the distance traveled by the solvent is this entire length. Let's just say that's 1.0. And then the distance traveled by the analyte is this length. And let's say that's 0.8. Maybe this is in inches, it's just arbitrary. So the RF in this case is equal to 0.8 over 1, which gives us a retention factor of 0.8. So to judge whether or not you have a good separation of your individual components, you want the retention factors to vary as much as possible. So in the A case, the retention factors are exactly the same, which means that you can't actually see the individual components, and the paper chromatography did not work well. But in B, the retention factors are much different. Therefore, that is a better paper chromatography method.